To give you guys an idea of where we are going in terms of the moment about a specified axis. When it comes to the moment about a specified axis, all we're going to be doing is something very simple. What we're going to be doing is the moment about a specified axis will literally just be equal to the dot product of a unit vector that points in the direction of that axis with the moment from, let me say, the moment, this of course, this is how we calculate the moment. So this of course looks a little bit weird when you just look at it here. So, but let me give you one example. A good example will be, of course, the questions that we're going to look at. But the best way to actually picture this is this unit vector that we have here. It's a unit vector in the direction of the axis we want to focus on, the moment about an axis. So this is the axis, a unit vector in the direction of that axis. But everything else here is exactly what we were doing last time. This is the moment about a specified point. But the only condition is that the point we're dealing with, that point, it must lie along that axis. So first, get the moment about a single point on that axis. Now, once you have the moment about a single point on that axis, get the unit vector that acts along that axis. Once you can do that, then you can get the dot product of that unit vector and the moment about a single point on that axis. That will give you the moment about that axis due to that given force. So if you were able to follow that, that's well and good. If you were not able to keep up with that description, we will still come back and analyze it. But in the meantime, let's try to work this question out so that we get in shape about the moment of a force about a specified point. Because even when you go to a specified axis, we'll still be coming back to the moment about a specified point. So in this case, we have this question where they say, determine the moment of a force F about the door hinges A and B. Express the result as a Cartesian vector. So for this part, I'm only going to work it out about the point A. After that, we're going to move on to look at another example, which is going to lead us towards a specified axis. But in the meantime, let's try to look at this question just for the moment about point A. So if we wanted to find the moment of a force F about point A, look at where the force is. So if I was to zoom in here, look at where the diagram is. Look at what is happening here. We have our force, and our force is this force here. This is where the force is. But we're given the force as just a value, 80 pounds. But you should understand to say that for us to actually evaluate these moments, the expression that we have for calculating the moment of a force, the moment of a force about any point will be equal to the cross product of the position vector running from where we want the moment to be evaluated with the force itself. So the force here has to be expressed as a Cartesian vector, and the position also has to be expressed as a Cartesian vector so that we can evaluate this cross product. Now, if you look at the force that we've been given, this force is given just as a value. It's not in Cartesian vector form. So we need to express this as a Cartesian vector. Then we need also to get a position vector R that runs from the point about which the moment is to be evaluated up to the line of action of our force. So how do we actually get to do all that? Well, we can start with which one here? Let's start with, we're going for A. This is to be evaluated about what? Determine the moment of a force F about the door hinges A and B. So let's pick a point. We can pick a point A that is somewhere here. So about a point A. So if I pick a point A here, and my force F is exerted at the point C here, So it means I need a position vector, or yeah, a position vector that runs from A going up to C. That's the one I'm going to use in my cross product here. Yeah, that's the one I'm going to use there. So to get this, I have to start from A. How do I reach point C? So to reach point C from A, how do I move? So I have to move from A along this axis, whatever it is, until when I reach this part. After that, I then have to move along this axis until I reach this point. After that, I then have to move upwards until I reach my C. So that is the displacement that I have to actually negotiate. Now, how do I move all this way? Now, you really have to pay attention to the smallest details when it comes to these diagrams. So if you observe the diagram the way it looks right now, so to move from A to this edge here, look at what you have to do. First, you have to cover this distance, this small distance, this 1.5 feet to here. After you cover this 1.5 feet, you then have to do this 5 feet that takes you from this point all the way up to here. Notice that it's indicated here that this all the way up to here, this is a 5 feet. So meaning you have to do the 5 feet plus the 1.5 here. That is what is going to lead you all the way up to here. And in what axis is this? If you look at this part, this is in the x-axis. So in the x-axis, you have to cover 1.5 plus the 5 feet for you to reach this edge that is right here. Don't get confused by the 1.5, which is here, because clearly from here, from this edge, from this part, it shows you to say that even that extra 1.5 is actually covered along, as in within this 5 feet. So all you have to do is include that 1.5, this 1.5 here, so that now you have a distance all the way from here up to this part. So along the x-axis, you have to cover 5 feet plus the 1.5. So once you picture that, so along the x-axis, you're going to cover a distance and the distance there. Okay, so along the x-axis, we are doing the 1.5 plus the 5 feet. So this is along the x-axis. And see what is happening. This 1.5 plus 5 feet, you're going towards the positive x. So here you're going towards the positive x. You're going to this direction, and this is the direction where the x is labeled to be positive. So that is a positive value. Another way that you can actually do this, I think Zumil actually prefers this second method, is just by indicating the coordinates of A and the coordinates of C, and then just subtracting them. C, the final, minus A, the starting point. That will give you the respective displacements that you have to do for each coordinate. But of course, I always prefer the motions for some reason, but I'll show you both methods. So here you've seen that in the x-axis, you're doing this sum here, 1.5 plus that, which ends up giving you, when you evaluate this will end up giving you a 6.5i. That is just in the x. But what else are you actually doing? So how about in the y-axis? The y-axis, if you come to our diagram, it's labeled to be this line. So along this line or parallel to this line, look at what you have to do. If you come back to our diagram here, the displacement you are executing parallel to that is actually just this piece. But is this actually given anywhere? It is not. But look at this. They've given you a 4 somewhere here. So it's now up to us to use the 4 and the angle they've given here to actually determine what this part here is going to be. So if I was just to isolate this triangle here, you must see that this is a right-angled triangle. So now I'm going to view it from this side. I'm just going to view it from the side. What will I see? So if I view it from that side, I have this, which is labeled as 4 feet. Then the angle here is labeled as a 45. Then my y component, the one I'm looking for is this one here. And the angle here is a right angle. It's a right angle. So to find this, of course, I see it side by side with my 45. I'm going to use cos. So it's going to be 4. Then cos the 45. This is what is going to give me my y there. Okay, so yeah, that is what is going to give me that piece of y. But what else? What else are we looking at? So that is going to give me that. Then the next part is we can also determine what this piece here is going to be. So that piece there, of course, it's just given by sine. So that is going to be a 4 here. And then we have a sine 45, this part. So this is going to give me the vertical part on the other side. Okay, but of course, you also have to remember that you're going in the negative direction. So just keep that in mind here. Okay, so can someone just evaluate what y cos 45 is? What the 4 cos 45 will give us? It's what? 2.8. So this is giving us 2.83? Yes. Okay. So what this is telling us is that this small piece here, this small piece is actually 2.83. So in the y-axis, observe the direction. Y is positive in this direction. Since you're moving backwards, it implies that you're actually moving negative 2.83. So I can remove this now. Move this away. So this is minus 2.83 in the j direction. Then the remaining one is now the y-axis, the z-axis, I mean. Parallel to the z-axis is the vertical one, this one. So, and notice that what you're doing parallel to that is actually this piece. And this piece was given by 4 sine 45. I expect 4 sine 45 to be the same as 4 cos. So it's also going to be 2.83. But since it's pointing up in the positive z, we expect that to also give us, but this time it will be plus. So to be plus 2.83 in the k direction. So of course, these displacements were given in feet, so you can just put that feet here. So we have our displacement vector from A to C. So that's the one that we will be using where we have R here. So to find, let's say, the moment about point A due to the force F, we're going to multiply. So the moment about point A will be equal to the displacement vector from A to C cross the force itself. So the force is pointing in this direction, so it will be cross the force. So this is what will give me the moment we are looking for. So I have now found what my RSC is. The only thing is, what is going to be my force here? So when I look at the direction of my force is running from A to D. So I need that force. It's running in this direction. So I need to find that force. It's given us 80 pounds, but that 80 pounds is just a magnitude. I need it in Cartesian vector form if I'm going to execute a cross product there. So I know to say, to write my force F that runs from A to D in Cartesian vector form, I can write it as a product of the magnitude with a unit vector that shares its direction from A to D. So any force can be written as the magnitude and its direction, which is just a unit vector there. So I need to find this unit vector because I already know what the magnitude is. Now, how do I get the unit vector that runs from A to D? So to get the unit vector from A to D, we're going to find a position vector running from A to D, then get its magnitude as well, divide it here from A to D. This is what is going to give us a unit vector. So we need to get the position vector or displacement vector running from A to D. Now, how do we get that? Well, we go back to our diagram. So we now want to run from A to D, not A to D. The force is from C to D. The force is not A to D, sorry for that. This is C to D. So I hope you guys saw that. It's important for you to get your directions right. So the force is running from C to D. There was a comment. Let me just see what the comment was. So the force was from C to D. So let's just make these corrections. Even the unit vector is from C to D. Okay, yeah. So this is C to D, C to D, C to D, and here. So we just want to be very, very careful. And you guys are here just in case I make such errors, be able to catch them for me. Okay, let's proceed. Okay, so we're running from C to D. So again, I'm taking C to D because the force is indicated to be in this direction. It's going in towards D at that point. So the displacement vector I'm looking for, it's a displacement vector that is also pointing in that direction. So to move from C going towards D, you can use the positions as well, or you can just make the motions as I indicated them earlier on. So you can just move from this point, you go down first. After going down, so of course that is going to be a negative. After going down, you have to move parallel to this axis all the way until when you reach this point. Then, once you reach this point, the last part will now involve you moving parallel to this axis until when you reach this. So now you would have reached your D. But what are you doing? How are the motions? Parallel to the x-axis, you did this. Notice that this time parallel to the x-axis, you just did that 5 feet. So if I have RCD parallel to the x-axis, you were going backwards. The x is positive in this direction, but since we are heading back, we'll take that as a minus. So that is a minus 5 feet. So this is in the x-axis, so you have minus 5i. The next part is, how about in the y-axis? In the y-axis, we did this much. And what is this much? Remember the first part, this side, we found this as 2.83. So it's the 2.83 up to here. Then the other side, we did this 3. So we're doing the 2.83 plus the 3. So this is what we're doing in the y-axis. And we're going in the positive direction. So this is going to be plus the 3 plus that is 5.83 in the j direction. Then the last part is in the z-axis. In the z-axis, we did this much. We were going down. And remember this part, we also found it as 2.83 in the previous part. So meaning it's a downward motion. So it's a minus there. So minus 2.83 in the k direction. So having found the displacement vector from C to D, we can then copy that and bring it here. So this again is RCD, not this AD we wrote earlier. Okay, so we have our RCD. The goal is to get the unit vector. So if we're going to use RCD to get the unit vector, we need its magnitude. So the magnitude of RCD will be given by, so you know how we get the magnitude. It's the square root of every bit there squared. So it's going to be minus 5. Don't forget to square the signs as well. So this is going to be 5.83 squared as well. Then plus minus 2.83 squared as well. So if you do this, what would be your magnitude? What would be the magnitude here?
$8.19.
8.19. Okay, so yeah, this is the magnitude that we're getting. So we can then get our unit vector. Our unit vector running from C to D can then be expressed as the vector itself, RCD, divided by the magnitude. So if we do the division, this is just minus 5 over 8.19 in the I plus, so I'm just dividing, this is RCD, so I'm just dividing every term by the magnitude. So plus 5.83 divided by the magnitude again, 8.19. This is now in the J direction. Then minus 2.83 divided by 8.19 in the K direction. So this is our unit vector. Once we have our unit vector, we can then get our force. Our force running from C to D, since it has the same direction as the unit vector, so you can write it as the magnitude of the force, which is that 80 pounds, multiplying our unit vector. Now, unit vector is minus 5 over 8.19 plus 5.83 over 8.19 J minus 2.83 over 8.19 K. So we can even distribute and divide. So distribute this and divide. So the first term will be negative 400 over 8.19. Divide by 8.19 as well. Negative 48.84I. Then do the same thing to the next one. 56.95. 56.95. Then lastly, 27.64. 27.64K. So we have got our force as well, and the force from C to D. The last thing, remember the goal was to get the moment about the point A. So we can then calculate our moment about the point, not O, about the point A. And the moment about the point A will be equal to the cross product of the position vector running from A to C cross the force running from C to D. This is the cross product that we are evaluating. We have every term that we need. You can do it the manual way, or you can use the determinant method since every term is represented here. So this moment will actually just be equal to the determinant of a 3x3 matrix, where you have your I here, and then you have your J here, and you have your K here. The only thing here is that you have to be very careful. For cross product, order is important. You can't swap them and hope to achieve the same result. What comes first is the position vector RAC. So you want to get RAC first, and RAC was this one here. So I'm just going to get this, and this is what is coming here. So this is my RAC. So I'll just remove what we don't need here so that I only need the values. Under I, this is representing I. Then under J, J is represented by minus 2.8. So I'll just have this under J. And lastly, for K, K goes with this one here. Then the next part now is to have the force. For the force, this is what we have. So get our force, and again, let's just bring it down here. Let's take it to shape. And looks like now it can fit. Okay, Now let's make sure everything is in place. So the I is not necessary here. This is positive, so it's fine. But this is negative. The negative must also appear. The K here is no longer necessary. So this is here. Get rid of that minus. The minus, just take it closer. Okay, so now everything is in place. We can then evaluate our cross product or our determinant. So our determinant, we know how it goes. Blind out the I, and what you're going to get is just going to be minus 2.83, multiplying the minus and minus, of course, will give us a positive. So I might as well just say positive here. So positive 27.8, that's point, that was point what? 27.6, 0.64. And then this is minus these two. So these two, it's going to be 2.83 by 56.95. All this, the unit vector it's going to have, it's the I that you silenced earlier on. The next part, when you move to the middle one, of course, you know to say it has to be now be minus. Minus what? Now I'm focusing on J, so it's no longer this I'm hiding out. I'm now hiding out this and this. So of course, I'm going to multiply the 6.5 with the minus 27.6. So I think instead of me doing this, you guys can just be multiplying them for me. 6.5 multiplying negative 27.64. What are you getting?
179.66.
179.66. Then minus, this is negative, right? Because this is negative 27.
Yes.
Then minus the cross product, the product of this and this, it's going to be minus. So the minus here and the minus on the middle will make this a positive. So just multiply 2.83 by 48.84. What will we get?
138.22.
138.22. And this has to be in the J direction. The last one is a plus. And again, now we are focusing on the K line. So it's this that we are forgetting for now. And just looking at these two. So the first part is 6.5 multiplying 56.95. What are we getting there? 6.5 by 56.95.
370.18.
370.18. Then minus. Now we're multiplying these two.
$138.22.
138.22. This is the K10. And yes, Chinanda, I've just seen your question. When we are using the determinant way to evaluate a cross product, the first one always takes this row. I hope that is what you are asking about. The first one always takes this row. The unit vectors will be on top there. So the second one here will always go last. You don't swap them. So I hope that was your question. Okay, so next up, we now want to simplify this. So go to the first term, this one here. Can you try to evaluate everything this part? What will we get in the I direction?
$65.86.
So that's 65? 65? No.
Negative 65.86.
That doesn't sound fun.
Negative 82.9.
Yeah, it's supposed to be negative 82.9.
Right.
Okay, so that's the first part. Now we simplify this one. Of course, we have this minus outside, so we have to think about it. This term will be negative, so the minus will make that a positive. So evaluate this, the term inside.
$41.44.
41.44. So of course, yeah, this will be positive. 41.44. Then next, the last part, what do we get there?
231.96.
231.96, so 232. So this becomes the moment about the point A. So if you need the units, just remember what you are multiplying. So the displacement vector had the feet, the force had the pound. So this is the pound multiplying the feet. So there we have it. This is how we get the moment about a specific point. The question, are we okay here? Yeah. Yeah. Okay. So yes, that's how it goes. So I hope this part is okay. And this illustrates everything that we actually need on this concept. Now we want to see how we can use the information or the knowledge that we've developed here to get in shape and be ready to look at that assignment question that we are about to start evaluating. So for that part, I have a question that I think I also did with the other group, but let's use it as well. It's something that is very basic, and it helps us really just understand what is happening. So let me bring it up, just a minute, it's coming. Okay, now we want to see how we can extend the same knowledge that we were discussing about moment of a force about a specific point to now cover for moment about an axis, a specified axis. Now, for us to understand that, well, we have one simple expression that we're going to be using, this part, which is an expression that I wrote earlier on as well. What you're seeing here is that to evaluate the moment of a force about a specified axis, all we have to do is, if A represents the axis that has been specified, then the moment that we're interested in is going to be equal to a unit vector that points in the same direction as that axis. This is the key part. It's the only thing that adds something new to what we are discussing earlier on. The unit vector here must point in the same direction as the axis. Everything else that follows here is literally what we are from doing. This is the cross product of the position vector R to the force. The only other thing that you must keep here is that this position vector, it must run from any point along this axis. So it must run from any point along the axis up to the line of action of the force. So this is the only condition that that you have to keep in mind. So again, for you to get the moment of a force about a specified axis, you must know at least one point on that axis. That point will be helpful for you to actually evaluate the moment about that point. Once you can get the moment about that point, next you can get the unit vector pointing along that axis, then get the dot product of the two, and you have the moment about the specified axis. So these are the techniques that we're going to be using. And a good example here is shown with this illustration here. If you look at this illustration, what they're saying is that we have a cube. And this cube, of course, the dimensions are said to be A here. Of course, you can give A to be a value for our discussion so that it doesn't remain too crazy, if I would call it that. So let's pick A to be some unit. We can pick a value for A. We can even say this cube has dimensions 2 each side. So I can say 2, I can even say 2 meters, 2 meters, 2 meters, and so on. And of course, our force P can remain as it is general, or we can even say, let's say A is equals to 2 meters, and I can even say that our force P is equals to 100 newtons, so that this question maybe doesn't look too theoretical. Now, how do we approach it? The first part, they're saying this cube is acted on by a force P as shown. Determine the moment of the force P about a point A. So our point A is here. And then we want to find the moment of our force P. Our force P is this side. So I want to find the moment of the force P about that point A. Now, I want you to understand one thing here. Zumila, you asked me a question earlier on. Is Zumila still here? Zumila, are you around?
Yes.
Okay. You asked me a question earlier on. I think we're having a debate about transmissibility to say, can we actually do this and so on? Well, a good example is this question. Since the technique we're going to use for this one, we'll come back also to that same question that you had. You see, for us to calculate the moment of a force about the point A here, we don't even have to shift this force and take it there. All we need is to get the position vector that runs from any point along our force A. We can even pick this point that runs all the way up to that point. Of course, it's not from F to A. It has to be from A to F, from the point where we are evaluating our moment to where the force is, or to any point along the line of action of our force. So we need the position vector running from A to F. So do you see that we don't necessarily have to change the position of the force F or the force P? All we need is the position vector running from the point about which our moment is being evaluated to any point along the line of action of our force. So in this case, the position vector will run from A to F, and the force P will remain rooted at point F. So with that specified, we need a few key things if we are going to evaluate this moment. So the moment about the point A, how do we actually get it? So the moment about point A, moment of course is a vector, so I might as well do that. It will be equal to the cross product of the position vector running from A to F cross the force vector P. Now, the force vector, of course, we can also say that the force vector runs from F to C. So we can still do this from F to C. So I can still do that as well for the force vector. So once we have this, we then want to just come up with what this is, and also come up with an expression for what our force vector is. So just like before, notice that everything we're doing so far is exactly as we did in the previous step, in the previous example. So to get our AF, so let's see what we're going to do. Here we're not it's not specified for us where our X, Y, and Z, where they are. So we might as well take the initiative of using the standard. So let's say our X will run something like this. Our Z will run vertical. And then our Y will run like this. Now, with the method that I like using a lot, I always shift this so that it comes at my starting point. Since I'm running from A to F, I'll put my origin so that it starts from A. And then when I start my displacement or my motion, I'm starting from the point A and I'm going to F. Notice that all I have to do is to move down in the Z-axis towards E. After that, I'll move from E parallel to the Y-axis until I reach F. Notice that I have I've already achieved that displacement from A to F just with this. So with this done, we can then come up with our position vector or our displacement vector running from A to F. In the X, we've seen to say that in the X, we actually don't do anything. We don't go in the negative X, we don't do this. We don't go in the positive X, we don't do that. So in the X-axis, we don't do anything. So that is a 0. But in the Y-axis, we move from E to F. That is along the positive Y. So if we take this notation where I was saying that take A to be equals to 2, so it would imply that this is positive 2I. Then again, let me just specify, these values are not present in the original question. I've just included them so that it's, yes, please.
So it would be wrong if I had to plane.
If you are to put it somewhere here,
yeah,
it will still be okay. It will still be okay. You'll still actually come up with the same results as we are doing.
all right.
Okay. So again, I was just specifying that the values for A and P are not specified in the original question. It's just me who placed them there because I feel it will be easier for you guys to actually understand what is happening. So that's a 2 in the I direction, not in the I. This is in the J direction. We said in the I, there's nothing happening. So this is in the J direction. So I have 2J. And then in the K, remember in the K direction, you had to go down. So in the Z-axis, you had to go down. So that is a minus. And since this is a cube, so it has to be a minus 2 as well. So this is going to be minus 2 in the K direction. So we have obtained what our RAF is. Once we've obtained what our position vector is, we now need to get what our force vector is. For our force, here I specified. Go ahead.
Why did you shift the axis to the point underneath AE? Or maybe you just you're allowed to shift to any point?
Yeah, you can. You can. You see, here, if you look at the way the question is, if I just did this, do you see that it's actually not there? The coordinate axis is not positioned anywhere. Do you see that it's not actually there?
I'm sorry, sir, I couldn't get that.
I'm saying that I've just removed all the lines I drew. This is the original thing, and these are the lines I drew. Do you notice that the coordinate axis is even not there?
Yes.
Yeah, so where I then draw it, it's completely up to me. So they didn't put it for me, so I can put it anywhere. But still, even if they had positioned it anywhere, the effect it will have, it will be the same. Even if I was to position it, let's say here, if I change my coordinate axis and positioned it here, moving from A to F would still be the same thing. Because look at this, if it is somewhere here, moving from A to F, notice that it's doing this. Moving from A to F implies moving like this. Even if I was to change my coordinate axis and bring it here, it will still mean the same thing. Let me show you. If I was to shift my coordinate axis, let me move this. If I was to shift this such that now it is here, moving from A to F would still mean coming from here and going up to there. It would still point in the same direction. So it would still be the same. Do you get that?
Yes.
Okay. Okay, so Chinanda, in terms of what we are crossing, it's the unit vector with the moment about a point. I'll get to it. You see, when we reach that step where we are actually doing that, I think it will be more clear to you what we are actually doing. So just hold on tight for that. It's coming right after this part. I think this part specifies that we are now getting the moment about an axis. And for this part, the axis is the edge AB. So that's the axis they are specifying. So we use that technique and you actually see how it works. So let's complete the first part. The first part is pretty much what we're doing in the previous example. What are AF? The next part is we need P, that's FC. For PFC, we need P itself, and then we need a unit vector that runs from F to C. So these are the two things that we need. P itself is given. I did give that 100 Newton, but we need a unit vector so that we multiply the two. So the question is, what is the unit vector running from F to C? So to do that, or to get this unit vector, just like before, we know to say a unit vector from F to C will have to be given by the position vector running from F to C divided by its magnitude from F to C. So this is what we need. So let's get the position vector or displacement vector running from F to C. So I keep interchanging position vector, displacement vector. I hope you guys are not confused. I hope you guys know exactly what I mean. Okay, so I'm running from F to C. How do I do that? So my F is down here. I can remove everything else. Notice that even without the coordinate axis, we can still do this. The coordinate axis is just there to guide us to say, when I move like this, it's x-axis. When I move like this, it's y-axis. But it's really not doing a lot here. So of course, I can put it here. I can even put it here. That's a funny thing. I can put it anywhere, and my results would still be the same. You can try with it here. You can try with it here. Now I am even bringing it here so that you guys can just see that we are free to even move it around and the results would be the same. For that analysis, it must just be there until I'm done with that analysis. So I'm moving from F to C, and notice that has nothing to do with the coordinate axis. All I'm asking is, how much do I move in the x-axis and how much do I move in the z-axis? In the x-axis, I move the full length of the cube at the bottom here, which is a 2, and I'm going in the negative x, so that is a -2. And in the z, I'm going again the full length, going upwards up to the top, which is the full length of the cube at that edge, so that's another 2, but I'm going up, so that is a +2. So for that displacement, we've seen to say that my displacement is in the x, I'm doing a -2. In the y, I am not moving at all in the y because my y is going this side or this side. I don't do this, I don't do that. So in my y, I am not moving completely, that's a 0. But in my k, I am going up, so that is a +2k. Once I have my displacement vector, I can get its magnitude. And you know to say it's the square root of each term squared. -2 squared, 0 squared, so I can skip it, 2 squared. Then this comes to give me, yes, please.
Just another question.
Go ahead.
So can we keep changing or rotating the axis in this in this question? Like what's enabling us there? How should we know that you can keep moving the axis?
Even if I left it here, perhaps I shouldn't have touched it. Let me leave it here. I've left the axis, I'm not touching it, and just observe, I'm starting from here. Regardless of where the axis is, do you see that in the x-axis, I'm still moving at 2 meters? Do you see that in the x, I'm still moving at 2 meters? Because from F to G is 2 meters. I am only moving the axis so that you can see clearly that this is the x-axis. My motion from F to G is the x-axis. That's the only reason why I'm moving my axis, to help me, not me really, to help you see, to say that, okay, when I'm moving in this direction, it's actually parallel to the x-axis. It's like when I move like this is the z-axis, and it's still a 2 because this is a cube. From G to C, it's a 2 meters. So I move the axis closer so that you can just see that. But even if it's there, provided you can still follow to say that's a 2, you should still be okay. Because see this is parallel to the z, and we are still going up. So this is still in the z-axis. And by magnitude, it's just 2 units in the z-axis up. So even if I didn't move my coordinate axis, notice that I am still achieving the same result. I keep moving the coordinate axis so that perhaps it becomes easier for you to follow what is happening. But even if you leave it in one place, you still achieve the same results.
I have a question.
Go ahead.
How is from G to C there? You've said that it's, we're moving in the positive direction. But when the time we move from E to A, you said it's negative. Now how are they different?
Okay, you have to be very careful. What you have said is actually correct. It's if you move from E to F to A, and you move from G to C, these two are the same in magnitude, and they even have the same direction, because in both cases, you are going up. But the one that was negative, if you followed, was from A to F. It's important where you're coming from and where you're going. From A to E, I mean, you're going down. From G to C, you're going up. Clearly, they don't have the same sign. Can you see that?
I thought we're moving from A to E. I didn't know that it's A to E, not E to A.
It was this one. We're doing this one. RAF. So we're starting from A. We were going to F. So we went down first, then we went to F next.
Thank you.
Okay. So in this one now, we are doing from E to F. There's another question? Okay, so we're doing from from F to C. So first we go to G. So this is, again, when you look at it, this is in the negative X direction. This is parallel to the X, so it's like we're going in this direction. Because of that, it's going to be a -2. And then the next thing is we go up. So since we're going up, this is going to be a positive Z. So this is the reason why we have a +2 here. So we quickly wrap up this. So this becomes a 4 here plus a 4 here. So this is just √8. So we have got the magnitude here. Once we've obtained the magnitude, we can then get our unit vector from F to C. So the unit vector will be FC. So this is going to be -2 over √8 in the I, then plus 2 over √8 in the K direction. So this is our unit vector. So since we now have our unit vector and we have the force itself, we wanted to use the unit vector to get the force. So where we have the unit vector here, we can substitute and get our force. So our P from F to C will now be equals to the 100 multiplying -2 over √8 plus 2 over √8. This is K, this is I. So what are we getting here? Multiply this, the 100 by 2 divided by √8. What are you getting there? or maybe we just leave it the way it is, minus 200 over root 8 I plus 200 over root 8 k. So we have got our force. So the last thing now is to get the moment. The moment, remember while we were doing all this, if we look at this, we now have the position vector from A to F. It's the first thing that we got. The other part was to get the force in Cartesian vector form. So this is what we're doing, and we have just obtained it. Now that we have the two, we can get their cross product so that we get the moment about F. So let me just copy my position vector. So this is what I am going to use. So my moment about the point A will be equal to the cross product of the position vector from A to F cross the force P that is running from F to C. So my position vector is this one. So implying that my moment will be equal to the cross product of 2j minus 2k, then cross the force vector, which is minus 200 over root 8 I plus 200 over root 8. Okay, so this is what we're going to do there. So of course, how you multiply this again, completely up to you. You can still use the determinant method. But if you feel this is more straightforward, you might as well just multiply them directly. If you feel this can be multiplied directly, let's actually try to multiply it directly so that you guys can recall that trick I gave you. So if you're going to multiply them directly, term by term, the 2 will multiply the first part. So this is going to be 400. So that's 2 by 200, that's 400. Then again, the order, it's j multiplying I. So this is j cross I. Then this is over root 8. Then next, the 2 multiplies the 200 this side. Oh, this was minus, by the way. This minus here. The 2 now multiplies the 200. So this is plus. Again, a 400 here. Then it's j multiplying k. That is j cross k. Then over again, root 8. Then the minus 2 multiplies minus 200. It becomes plus 400. Then it's k multiplying I. So that's k cross I divided by root 8. Then lastly, you have the minus 2 multiplying the positive 200. That is minus 400. And then you have over root 8. Now again, the unit vectors, it's k cross k. So this is going to be k cross k. So if you looked at these unit vectors, one simplifies automatically. When you look at this, what will be k cross k? What is k cross k? So this term disappears instantly. So we only have to worry about these 3 terms here. So we now want to know what is j cross I. What will be this? So we now want to know what this will be, also what this will be, and also what this will be. So what is j cross I? So the quickest way I gave you guys to remember them, someone wanted to try? Go ahead. Negative k. Okay, let's see. The quickest way I gave you guys to try them, you have I cross j cross k, then just repeat the I at the end. So if it's I cross j, these two, the answer you get is going to be k. Then if it's j cross k, the answer you're going to get is going to be I. Then if you get k cross I, the answer you're going to get is j. The reverse is negative. J cross I is negative K, K cross J is negative I, and I cross K is negative J. Yes, please.
My internet dropped. We didn't use the cross product.
No, I just went directly so that I think the second group, I did show them this trick. So I thought I'd take advantage of your presence, you guys. You guys in the first group, I think I didn't really show you this funny property of how you can mix up the unit vectors to see how they cross without using the hand rules. You can use the determinant method, you still get it, but I felt like since you had only 2 terms here and 2 terms here, it was easier to just multiply directly. Okay. So if we use this trick that I've just illustrated here, you quickly see that it literally simplifies the problem instantly, because J cross I, when we check here, it's the reverse of this one here. Since it's the reverse, the answer has to be negative K. So we know here we're going to have negative K. Then when we look at J cross K is the forward of this, which is fine. So it's going to give us I. This will simplify to just give us I. Then you have K cross I. K cross I is okay here as well. It gives us J. Had it been I cross K, would have ended up with negative J. But currently it's fine, so this will give us J. So then we can easily simplify our problem. It becomes, since this is negative with the negative outside here, the whole thing becomes positive. So we now have positive 400. The unit vector is now a K. This is over root 8. Then we have the next one here. It's 400 over root 8. Over root 8. And the unit vector there is I. Then the last one here, it's 400 over root 8. And the unit vector there is J. So you have this. We can rearrange this so that we have literally 400 over root 8. I, J plus 400 over root 8 K. That is how we work out that problem. Any questions there? So notice that this is just the moment about point A. Now this is where we go towards the moment of a force about a specified axis and see how it works. Now, the question that follows, let's see it. In the question that follows, they are asking us to say, determine the moment of P about the edge AB. So everything else that will follow, you guys, is going to be less involving than what we've done. The hard part was just that first part. So we now want the moment of the force P about the edge AB. So where is AB? The edge AB is this one. This is the edge AB. So remember how we get the moment about an axis, because the edge AB is literally an axis. So that axis, we need a unit vector that runs along that axis, because the moment about an axis is equal to the dot product of a unit vector that runs along that axis with the moment of the force about any point along that axis. So you see, any point that lies along that axis. So this part here is just determining the moment of a point. Once you get the moment of a point, get the dot product of the moment of the point with a unit vector that points in the same direction as an axis. The only condition here is that the point that you use, it must lie along that axis that has been specified. A good example is our current question. In our current question, notice that we need a point that lies along the line AB. But notice that the previous question we were working out, it actually used a point that lies along this line. because we determined the moment about the point A. Notice that the point A lies along that axis. So because of that, we already have the moment of the force P about a point on the axis. In other words, we already have this part sorted out. This moment about the point A lies on the axis AB. So this actually tells us the moment about a point on that axis. The only thing that we now need is a unit vector that points in the same direction as that edge AB. So what do you think is the unit vector that points in the same direction as the edge AB? So if you look at this, what do you think is a unit vector, will be the unit vector that points in the same direction as the edge AB? What do you think?
What are which one?
Let's, yeah, it's what? J, yes. So you have to see that this axis AB, it actually lies parallel to the J axis. In other words, it has the same direction as the Y axis. So a unit vector that runs from A to B, it will actually be the same unit vector that runs in the Y axis. In other words, the unit vector in the Y axis is actually just J. So because of that, our unit vector along our axis, our desired axis, that unit vector is actually just J. Because of that, our moment about the specified axis now, the axis AB, this moment will actually now just be equal to the unit vector that we are dealing with, J, then dot, the moment about any point on the axis. We got that moment and it was given by this, which is 400 over root 8, I, 400 root 8, J plus 400 over root 8, K. So this is all that we have to do. And we know the property of dot product. J dot I will give you a 0. J dot J will give you 1. J dot K will give you 0. In other words, when we distribute this times this times this, and then this times that, all these will give you zeros except where you have J dot J. So the answer here ends up being a 400 over root 8. The J dot J will give you a 1. This becomes the moment here. One other thing here is that dot product between two vectors will always give you a scalar quantity. That is why this doesn't have a J, doesn't have an I or a K. It only comes out as a number. In other words, we can make a conclusion. The moment of a force about a specified axis is actually not a vector quantity. It will be a scalar quantity. So I hope that is actually okay.
I have a question.
Go ahead.
Okay, it's not really a question. Can you kindly explain how this second formula relates to the first one? Because the second formula is moment about the specific axis and the first.
Okay, so here's how it goes. In the first part, you have a point. Then you have another force. Let's say you have another force here. You have a force here. Your force is F. You want to find the moment of the force F about our point here, O. So what you need here is the position vector running from O to anywhere along the force F. This position vector, we call it R. So to get the moment of the force F about the point O, we just say the moment of the force F about O will be equal to the cross product of the displacement vector running from O to anywhere along F cross the force F. This is the first part. This is what we did in the first part. But now, to get the moment of a force about a specified axis, here's what we need. Let's say this is the axis, and now I'll make it that it's not along the x-axis or the y. Let's say this is the desired axis. And you want to get the moment of a force, and let's say maybe this is our force here. So this is our force. To get the moment of our force here, F, about this given axis, let's say my axis is labeled, let me say, K. About my axis, maybe K is not a good term. Let me use my axis B. To get my moment of the force F about the axis B, what I need is a point, a single point along B, along the axis. My point can be here, it can be here, it can be here, it can be anywhere. All I need is one point along my line B. Once I have that point, the first step, let's say this is where my point is. The first step involves me evaluating the moment of the force F about that point that I've identified on my axis. So the first part is just R cross F, where this R is from a point that lies on my specified axis. So this is the part that relates to the earlier methods we were doing, moment about a specified point. Once you have evaluated the moment about a point that lies on the axis, then get the dot product of this moment with the unit vector that points in the same direction as the axis. So this is a unit vector that points along the same direction as our axis. So let's say this unit vector points along the axis B. Have I answered your question, Mapang?
I think so.
You think so? I haven't.
Some questions later on.
Okay, so a good example again would be this one here, this question we're working out. The first thing that we did was to get the moment about a point A. We were doing this, still our goal was to get the moment about this line AB. But we needed first to evaluate the moment about any point on the line AB. And luckily for us, in the first part, we got the moment about this. Notice that we could have easily got the moment about this point and still used it, would have got the correct answer as well. So we only need one point on this axis. Once you have one point on the axis, get the moment about that point by using the position vector. Once we have the moment about one point, multiply the moment about that point, of course, dot product, by a unit vector that points in the same direction as the specified axis. In this case, the specified axis was this one. What could have been our approach if the axis was different? If the axis was different, we would have been forced to find a point that lies on our new axis. Notice that the next question, I will continue answering that question. The next question here, AG. If you look at this question, now they're saying about a diagonal AG, meaning from A to G all the way up to this point. Notice that in this case again, this axis starts from A, meaning we can still use the moment about the point A in the first part. Remember again, we need two things, the moment about a point on our axis and the unit vector in the direction of the axis. So for this part, the moment about a point on the axis, we will still use the first one that we got because A still lies on the axis AG. The only thing that we now have to determine is a unit vector that runs from A to G. Had it been that they want us to get the moment about an axis, let's say let's say even, maybe not EC, let's say ED. If they wanted us to get the moment about the diagonal ED, we would have been forced to first calculate the moment about the point E, or if not E, would have been forced to get the moment about the point D. So all I'm saying is we would have been forced to calculate the moment about a point that lies on our line ED. After getting the moment about a point on our line ED, then would have got the unit vector pointing from E to D. Excuse. Then lastly, get the dot product. I hope I've answered the question, Chinan. Okay, great. So let's finish it up. So for the second part, the third part, I mean, from A to G, we need the displacement vector from A to G. We already have the moment about a point on that axis. So to specify what I'm talking about there, we want to get the moment about the axis AG. That's AG. Let me look at it. Yeah, that's AG, about the diagonal AG. So to do this, we need a unit vector that runs from A to G. Then its dot product with the moment of the force about any point on our line AG. Luckily, we still have the moment about the point A. So we'll say the moment about the point, perhaps instead of doing this, let me just say the dot product with the moment about the point A. A lies on our diagonal AG, so A works. And remember what this is. This is R, A, C, cross F, C, F. We already did this. Not F. It wasn't AC. It was AF cross F. It wasn't F, it's P. P, FC. We already did this. This is what gave us the moment about the point A. So all we need again is a unit vector from A to G. That diagonal we are looking for. This is not AG, AC. This is AG. So we need a unit vector from A to G. To get this unit vector, we need the displacement vector that runs from A to G divided by its magnitude from A to G. Okay, is it something that we need to continue with? Or you guys get what we have to do? Should we continue with this, or you guys understand what we have to do now?
Continue.
Okay. So let's get RAG. So RAG, let's see how it runs. So to move from A to G, notice that first we can say we go down 2 meters down, then we go 2 meters to F, then 2 meters to G. We would have reached our G. This is 2 meters in the K direction. Because it's down, it's negative. Then this is 2 meters in the J direction, it's positive. Then it's 2 meters in the I direction. We're moving backwards, this is negative. So you've seen our displacement. Our displacement from A to G will be negative 2I, and then plus 2J, then negative 2K. This is our displacement vector. So once we have our displacement vector, I hope you guys are seeing how straightforward this approach is. And I hope, Zumila, you're seeing how easy this one is if you understand how to use it, how easy it is and how quick it is, unlike getting the coordinates of each of the two endpoints and then subtracting them. That one can be a little bit longer. But if it's I think the only benefit of that is it's a little bit more clear that it's hard for you to make mistakes. This one, you really need to understand what you're doing. So from here, the next thing is we can get our AG. So this is going to be 2 squared, which is 4. 2 squared there again, another 4. 2 squared there again, another 4. So this is what we're getting. So the 4 added, that's going to be a 12. So we're looking at root 12 here. So once we've got our magnitude, we can then get our unit vector. So the unit vector that runs from A to G will just be equal to our AG divided by all this. So remember how we're getting the unit vector? It's just this one. So I can say my unit vector will be each piece divided by root 12. Then plus, that's now 2 over root 12. Then minus 2 again over root 12. So that is my unit vector. Why did I need my unit vector? So that I could get its dot product with my moment about A. So since I now have my unit vector and my moment was calculated earlier on, I can bring them here and now substitute. So my moment about the axis AG, that's not a vector. This will be equal to my unit vector, which is minus 2 over root 12, plus 2 over root 12, minus 2 over root 12 again. Then the dot product with my earlier moment about A. And this was my moment about A. So this was my moment about A. I've just copied it from where we did it earlier on. So once we've done that again, this is a dot product I am evaluating. This is my moment about the point A. And this is my unit vector pointing in the direction of AG, in the direction of my axis. So the last part, multiply like for like again. This is a dot product. So 2 will multiply the 400, so that becomes 800. Of course, this is positive, this is negative, so this is going to be minus 800 over root 12 multiplying root 8. Then this is going to be plus the 2 over root 12 here. J will multiply the 400 over this. Again, it's like for like. This will still be 800 here over root 12 again, multiplying root 8. And then next, I'm doing this and this. So this is going to be a negative because I'm seeing a negative here. So it's going to be minus 800 over root 12, and then root 8. So when I see this, I can argue to say that one of these pairs is going to subtract out so that my final answer will just remain as minus 800 over root 12, root 8. So I can conclude that this will be my answer. Is that okay? Of course, these roots can be simplified. You know, to say root 12, this can be written as root 3, root 4, root as in root 3, root 4. Yes, even this one can be written as root 2, root 4. So yeah, these can be simplified. I just hope we didn't make any silly mistakes in our evaluation. But otherwise, this is the answer that we're going to get. Okay, so should I simplify this or you guys get it up to now? This is fine?
Fine.
Okay. So there we have it. That part is done. Okay. The next part here is the last one. Look at the last one. The last one actually will also be helpful in you evaluating one of the examples, one of the questions in your assignment, where they wanted you to get the distance D. So this is one of the tricks that you're going to use in terms of getting it. So determine the perpendicular distance between AG and AF. So where is AG? Where is AF? AG is this one. AF, that's not AF, is it? AG and FC. FC and this one. The perpendicular distance between them. So if we wanted to find the perpendicular distance between these two, we want to use a trick here. But the trick that we want to use depends on one thing. Depends on the fact that FC is actually perpendicular to AG. So the first thing that we want to do is to test it. Is FC actually perpendicular to AG? Because the method that we want to use just deals with one thing here. If let's say they are perpendicular, then the moment about that axis AG, so the moment about, the moment about the axis AG, not its direction and so on, just its magnitude. If let's say those two are actually perpendicular, the AG and also the force running from F to C, if the two are perpendicular, then the moment can also be calculated by just multiplying the force P by the perpendicular distance between them. You see, if they are actually perpendicular, then we can get the same answer by just multiplying the force 200 by the distance between them. Oh wait, was my force 200? I think I gave 100 for the force. It was 100, I think. Yeah, I gave 100 for the force. So P is 100. So we can get the same moment by just multiplying the force here, which is 100, by the distance between them, which is D. Now, we want to utilize the fact that we already know the moment that we have, and of course, just the magnitude. So we would be able to just say that the moment, which is 800, divided by root 12, then root 8, this will have to be equal to just 100 times D, yeah?
This is the last question about the particular distance.
Yeah, this is the last question.
Can you kindly start, or I got disconnected?
Okay. So, yeah, it starts somewhere here. So what I was saying is that to get the perpendicular distance, if two lines are, if you have lines like this, and then I gave you a force, and I told you to say that this force is actually perpendicular to the distance. If I give you the distance from here to this point, and I say that these two are perpendicular, if this is a distance D and this is a force F, and I asked you to get the moment about this line, or to get the moment even about this point F, if the two are perpendicular, then you can just multiply F times D, and what you get is going to be your moment M. Now, in this case, what we're given are two lines which are not close to each other like this. But what we are seeing here is that if we look at this diagram here, what we're seeing is that our line AG is actually this side. This is where AG is. And our line FC is this one. So we want to see if they are perpendicular. If they are perpendicular, then that simple approach of force times perpendicular distance will give you the moment, will work. So if these two are perpendicular, then you can just say the force times the perpendicular distance is actually equal to the moment. But to see if they are perpendicular or not, we will use the dot product. But what I was doing is that I'm first showing you the technique we're going to use to get the distance, if it's true they are perpendicular. So I was saying that if they are perpendicular, then we can say that the moment will be given by The moment about AG, because of that force P, will be given by just the product of force times the perpendicular distance between them, such that the force is 100, the distance between them is what we're looking for, D, the moment is MAG. Now, we already calculated what the moment is going to be, so I just brought the moment here and the 100 is to here. So 100 here goes once, it goes 8 times into 800. So we'd have 8 over root 12, then root 8 here. Then this will actually be what our distance will be. So we're saying our distance D will be equals to 8 over root 12, then root 8. Of course, you can simplify this. I gave my distance there to be in meters, so let's say this is going to be in meters. But this is only true, this approach is only true if the two lines FC and AG are perpendicular. But how do we know whether they are perpendicular or not? To show whether two lines are perpendicular, all you need to do is just get their dot product. Now, the dot product of what? Just get two things. You just need two things. You just need two vectors that are running along each line. We already have the force vector running along FC. So you can use the force vector there. And we also still have the unit vector that runs from A to G. So you can use the unit vector that runs from A to G, get their dot product. So I can get the dot product of A. Let's see. Yeah, I can get the unit vector of A, FC, dot, the force that runs. You can use the force, or you can as well just use, I think there was a time we actually got the unit vector from F to C. You can also use the unit vector that runs from, wait, I've written F to C. And it doesn't matter. I say the unit vector from A to G dot the unit vector running from F to C. What you'll see is that if this gives you 0, then you can conclude that these two lines are perpendicular to each other. If it doesn't give you 0, then they are not perpendicular to each other. You guys can try it out. You will see that it will give you a 0. And once it gives you a 0, then this method we just used here actually works to give you the distance between them. I rushed to finish this one so that I can ask you guys one question. Do you have enough juice to continue and do the assignment, or we leave the assignment question for tomorrow night?